Good afternoon, good morning, everyone. My name is Amarjeet Singh. Today, I'm going to present leveraging modern network to deliver faster storage to database workloads in Kubernetes. A little bit about me. I work for a company called Kioxia America. Within Kioxia, I am in Kumoscale business unit, which offers NVMe over Fabric software storage solution. I'm Solutions and DevOps Engineering Director over there. This is my Twitter handle if you want to reach to me directly. In this talk, I'll start with advancements in storage and network technologies. Then we will introduce StatefulSet applications in Kubernetes. We'll talk a little bit about those applications. Finally, we will put together everything and see at a bigger picture, followed by a demo. So please stay in tune. All right, let's talk about storage technologies first. Speed, capacity, real estate, along with its location, either local or on the network, are three important aspects of storing data. So we saw availability of altogether of a new protocol after 25 years. SCSI came into existence in 1986. Then after about 25 years, we see NVMe protocol. We'll talk more about them in the upcoming slides. And then historically, as we saw NVMe protocol during the same time frame or like few years here and there, we saw that RDMA over Converged Ethernet version 2 came in 2014. We'll discuss about this a little later, but it's a technology to deliver storage from server to a client over the network, over a faster network. And then the technology to deliver NVMe protocol over the Ethernet or over the fabric, not only Ethernet, came in 2016. And then during the same time, Linux kernel started supporting out-of-box modules for NVMe over fabric delivery of storage. Disk drives evolved from spinning to solid-state based disks. So when disk drives evolved from spinning to storage to solid-state disks, they demanded a new protocol, and that's why NVMe protocol was rewritten from ground up. We'll compare it to the other protocols in the upcoming slides. So at a very high level, a quick comparison shows us that NVMe drives are almost directly connected to PCI bus or directly connected to PCI bus. Hence, there is not much latency or loss of performance. While other technologies like SCSI and SATA, they were connected to PCI bus through some other building blocks and hence were not able to deliver the performance that PCI bus can offer. So if we compare it from a user perspective or from an application perspective, let's see how the performance changes, right? So spinning drives, SATA or SCSI, they used to give some performance. Let's keep that as a baseline. In the chart, what is shown is that when media changed from spinning drives to flash drives, there was a significant improvement in the performance. Lower bar is better. So when the protocol along with media changed from SATA or SCSI to NVMe, the performance improved much more further. So we see lot less latency, and hence we have more room for more IOPS and bandwidth and all that. So let's look at these technologies or protocols, SCSI and NVMe. If we look at SCSI, there are two aspects in this storage protocol. One thing is storage commands. How many storage commands can be basically queued in one queue? That's one aspect. In SATA or SCSI, depending upon like their version or what type of hardware and all that, so you can have up from 32 to 256. Let's say the standard is 64 queue commands in one queue, and these technologies, they offer only one queue, while in NVMe you can have up to 64,000 queues. So that's a big change. And not only that you can have 64,000 queues, but each queue can handle, each queue can have 64,000 commands. So this increase in capacity, not the storage capacity, but the capacity to transfer data, basically can enhance performance or has enhanced performance big time. That's where the performance of a much better performance of NVMe protocol comes from. Now let's look at networking technologies. So what has been happening on the networking side? 10 Mbps was the fastest network speed when SCSI protocol came during those times. Today, we're talking about 100 Gbps network speed. It's such a huge increase. So if this network throughput has increased so much, or underlying hardware is capable of transferring such a huge data, should our protocol not be able to take advantage of that? Yeah. So that is why newly developed protocol, as we discussed earlier, NVMe, can take benefit of those technologies, and we'll put everything together. Since this talk is about taking storage from a storage node to the client over the network, let's refresh our knowledge about networking technologies. As we know, networking technology, when we discuss about networking, it's usually discussed in terms of 7 layers. Each layer has a way of transferring data using its protocol. For example, there are protocols like TCP, IP, Ethernet, SSH, HTTP. They all work at various different layers. So similarly, the RDMA is carried over layer 2. So RDMA is a technology which basically gives remote access to DMA for one node to the other node, so that anything in between to transfer data to the memory can be bypassed. So that way you don't have to put load on the CPUs. The remote systems, they can directly access memory. TCP/IP is a standard protocol in data centers, in homes, in our mobile phones, or everywhere. So that's how multiple compute nodes, whether they are storage nodes or worker nodes, they connect to each other. Ethernet is the lower level, layer 2 data link layer protocol, which basically is widely used in data centers. That's how you connect various computing nodes. So, all right, now we talked about networking, we talked about storage technologies. Let's try to put these things together before we combine them with the modern cloud technologies. What is NVMe over Fabric? NVMe over Fabric is a way of sending NVMe commands over network. It can be an Ethernet network, it can be fiber channel network, or there are a few others supported. But for the simplicity and for the scope of this talk, when we say NVMe over Fabric, I want to refer it to Ethernet. So as we discussed earlier, NVMe protocol can have 64,000 queues. Each queue can carry 64,000 commands. Now, sending those queues and commands in those queues over network is called NVMe over Fabric. So your both ends, like your target storage node side and the client, we can also refer to client as an initiator. They both should understand it, how to send those commands and how to receive those commands. Since underlying network is very fast and there are technologies like remote DMA available, so the sending commands over network, NVMe commands over network, is very efficient. So this makes it remote block device look like a local block device. It appears as a local device, but even the performance that it provides is of a local block device. I'll show you a comparison a little later. And then latency is very low because the changes in protocol, changes in network, all putting together, they enable delivering faster storage. So since the performance of remote storage is almost like that of a local storage, so you are not losing on the performance, but at the same time you're gaining on the flexibility of centralized or disaggregated storage. So this is a view to show you how a storage target on one side, left side, and storage client or a client node, they would communicate over network, and so how client can access remote NVMe over Fabric device over the network. Since the protocol optimizes, PCI is directly connected to the remote NVMe disk, and on the client side, the protocol and then the remote together with RDMA can basically minimize number of blockages or number of layers between the storage traffic. So the performance is enormous. It basically is like local disk performance. All right. So when you deliver block devices or NVMe over Fabric from a target node or a storage node to a client node, there are two ways of delivering it. One way is using RDMA over converged Ethernet, and the second way is using TCP. So remote DMA bypass a lot of unbundling between client and target. So that technology basically takes the performance to a very high level. So RDMA over converged Ethernet technology gives much better performance because the components like CPU, they don't need to do any work. They don't need to do much work for carrying the protocol or for translating or packaging, unpackaging some of the aspects. So that's why you get a high performance. But at the same time, it requires a special NICs. So that's where those tasks are offloaded to. But on the second method, which is basically using the TCP, TCP is standard in data centers. Your compute nodes are already connected. There are already TCP. There are already standard switches, already standard protocol stacks, technologies available, softwares, drivers, everything is available in the clients and clients, switches, routers, and everywhere. So if we leverage TCP and send NVMe over Fabric commands over TCP, then we can use it with simplicity. But at the same time, some of the work which was earlier in RDMA offloaded to specialized NICs is now performed by CPU and other components within client and storage nodes. So that's why TCP gives you less performance, but it is easily doable because your standard data center is already connected through TCP. So you don't need specialized hardware. Let's look at performance comparison of a local NVMe drive and a remote NVMe drive. So if we look at how much, what is the difference between latency, IOPS, and throughput when measured for a local disk, and then when measured with the NVMe over Fabric remote disk. So these numbers, they show that the difference is so small that a remote NVMe over Fabric block device gives performance like a local NVMe drive. All right, so enough about storage and networking and putting them together. Now let's talk about the use cases in the modern cloud technologies. Kubernetes. Kubernetes is a container orchestration framework. Basically, it spins up containers and then it makes sure that X number of containers are always running. If they are not running, if something goes on, it ensures that new containers come up, or if you want to scale down or scale up, it can keep up with that pace. This all started with basically availability of LXC containers in 2008. Kubernetes did not come in at that time, but at least the fundamental building block, which is container, they started to appear in 2008. And then Docker's simplified building images which can run containers easily. So that happened in 2013, and then the next problem was how to ensure that all those containers are running, scaling up, scaling down. That's where you need Kubernetes. So Kubernetes came in 2015 with version 1. Now you have a way to run containers. You have containers and a framework to orchestrate those containers. But then what applications you run in those containers? Applications can be stateless application or stateful applications. Stateless applications are those applications which don't save data. Stateful applications are those which save data and retrieve that saved data. So we'll talk a little bit more about them. Kubernetes started offering full sets in 2016 so that customers can run their stateful applications. And then, since the stateful applications need a way to store and retrieve data, so they need basically volumes or block volumes at the backend. The way the stateful set applications or containers access those block volumes, persistent volumes, is through CSI driver. And CSI driver became GA in 2019, very recent. So now all these things happening in the modern time, if we put them together, this is the right time to leverage storage technologies, networking technologies to run your modern applications. Let's talk about workload types in Kubernetes. I already touched upon them. So stateless applications, they don't require persistent storage because you don't have to store or retrieve a storage. Think about an application server which gets a request from a user to pull, let's say, an image. If user want to see an image, all that application server does is it goes to the image storage place, pulls that image, and provides this to user. If that application server goes down, that image which it pulled is already saved somewhere. It doesn't belong to application server. You can restart or you can start a new application server which can also pull the same image. So that's how stateless applications work. They can be terminated and restarted at any time. On the other side, stateful application, they require persistent storage. In the example that I quoted, image has to be stored somewhere. So that is stateful application. If it is not image, if it's a database, then it's a stateful set application running database. They basically can be terminated, but when they restart, they need access to the same storage. Right? All right. So stateful workloads in Kubernetes, they are mostly for databases. They require permanent storage. And permanent storage within Kubernetes world is provided by persistent volume through CSI driver. So performance and flexibility of stateful set persistent volumes is important. So how databases access those volumes, and if a database container goes down, it needs the same persistent volume next time. So that flexibility is very important. And at the same time, they need high performing storage. So we'll see that in a demo coming up. So what are some of the stateful set applications? MySQL database, Cassandra, NoSQL database, Kafka, all these are stateful set applications. All right. Now, stateful set, how you run stateful set applications in Kubernetes is via stateful set objects, right? Stateful set. They create containers or pods in Kubernetes. Containers run in pods, so they run stateful set controller. There is a stateful set controller in Kubernetes which runs stateful set containers. So before Kubernetes version 1.5, stateful set was called pet set. If you recall, pets and kettles, the pet sets came from that. After Kubernetes version 1.5, they were renamed to stateful sets. So when you run stateful set workload in Kubernetes, what are the challenges? In databases, especially in SQL databases, there is a concept of master and slave. Master, you can write to master, you can read from master. but you cannot write to slave, because if you are writing to slave, it doesn't. There is a problem with the consistency. So there is always a challenge of coordination between master and slave, especially when you run in containers. And if one goes down, how you basically bring something else up as master. Uh, the replication, right? So when you have multiple nodes, whether they are SQL Server, NoSQL, or any other stateful set workload, you want to keep multiple copies of the data. How you replicate data across the nodes is another challenge. And if there is a corruption in data, how do you detect it? And then the other thing is, in stateful set applications, if you recall CAP theorem, which is basically your database has to protect the database need to be protected. So one of the aspect is, if one node goes down, how database handles availability and partitioning. So that's what you need to test, and Jaspen is one of the tools which you can use to test. All right. So now we talked about types of stateful set stateful applications. They run as stateful set objects or a stateful set containers or pods in Kubernetes. But those pods, those containers, they need persistent volumes. Those persistent volumes can come from local node. When I say local node, so Kubernetes has a concept of worker node. Worker node is a server which runs your containers. Container in Kubernetes is run in a pod. One pod can run one or more containers. So those pods, they're on hardware servers called worker nodes. So persistent volume or the storage for those pods can come from local node, from a local disk, or it can come from a remote disk. So you can have a centralized storage like NFS, Fiber Channel, or NVMe over Fabric, anything that can provide storage to all the worker nodes, or many worker nodes, or some worker nodes, instead of each of them getting that persistent storage from their local drives. So CSI driver, which is like container storage interface, provides a way to provision persistent volumes, and also depending upon type of storage you use, and the ability to move around persistent volumes. That's what CSI driver basically offers in Kubernetes. It is basically an interface between Kubernetes, so that Kubernetes can assign persistent volumes to pods, to on the other side to the storage where the volumes come from, even if they are coming from local disk. Let's see, putting this together. So as I said, I work for a company called Kioxia, and we have a software product called KumoScale. So KumoScale is a NVMe over Fabric storage cluster, which provides block volumes over Fabric to clients, right? Using leveraging all the technologies that we discussed so far. So your clients, whether they are Linux clients, or they are worker nodes in Kubernetes, or they are nodes in OpenStack, can access centralized storage or disaggregated storage. And as we discussed earlier, since we deliver storage using NVMe over Fabric, so the performance that clients see is almost like a local disk performance. So for the sake of this talk, let's focus on the Kubernetes. So in this architecture, you will see that there is one storage node or one storage node cluster, and there is a provisioning service, and there is a CSI driver, and on the left side we have multiple Kubernetes worker nodes running containers. So when Kubernetes need to run a container or a pod, it talks to it talks to the provisioning service via CSI driver that okay, I need these volumes. I need to have this much volume, and then provisioning service provisions those volumes on the storage node, Kumo scale storage node in this case, and uh, gives or provides or attaches that volume to relevant worker node so that pod or container running on that worker node can access that volume. Uh, Now, let me show a demo. In this demo, what I will show is that we will create a Cassandra cluster. That cluster consists of three instances of Cassandra. We'll create volumes, not manually, automatically, uh, via provisioning service, and we'll see how they're getting created. So those volumes will be attached to three instances of Cassandra running in pods or as containers. And if one of the pod dies and moves or gets started on another hardware server, the storage which it had earlier moves there, and we will verify that it is the same storage volume. So let's go through the demo. So basically, on the left side, I'm showing number of volumes on the storage node, nothing at zero at this time. On the right side, on the top window, I'm showing worker the pods running, and then the CSI driver, and the lower window where I'm running the commands. So first, I'm going to just create a cluster, Cassandra cluster of three instances. We see that as soon as I created the first Cassandra instance started, and it created a volume. So who created the volume? Provisioning service, which is called through CSI driver automatically. Users don't do anything. So as that volume is created and attached to that instance, which is running in a pod, we see that instance is running on node 3. Now, node 3 in the lower part of upper right window shows that node 3 has now one NVMe over fabric block volume. So as soon as first instance of Cassandra becomes available, the Kubernetes will start second instance. This is called basically these instances are started in sequence, although there is a way to start them in parallel at one time. All right, so first is ready. Now the second one is getting started. Second one is getting started on node 4. As soon as Kubernetes scheduled it, so there was a new volume created. We can see that on the left side. And on the right side, that we can see that now Kubernetes server node 4 has a new volume, NVMe over fabric block device. And when this becomes available, when the Cassandra instance -1, which is the second instance, is ready, Kubernetes is going to start the third or the last Cassandra instance. And at that time, we will see that on the left window, there will be one more volume, which just appeared. So now we have three volumes created on the storage node. And as we see, the third instance of Cassandra, the third container, is started on node 5. So node 5, if you see, now has a block device. It did not have earlier. So these commands are running continuously on these nodes. And it's a watch command. So as soon as this third instance is ready, we are done with starting the Cassandra cluster. And then we'll move to the second part of the demo, which is basically Okay, so let me take a pause here. So in the lower bottom window, you will see that three PVCs, persistent volume claims, which are mapped to persistent volumes, are shown in Kubernetes, and their name is the same as you see on the storage node. All right. So now let's move our Cassandra instance -2 to another node and see what happens. So move basically is a script which runs one by one. Basically, what it does is it's on Cassandra -2 instance. It's first going to create a file, because right now this instance runs on node 5. We are going to create a file, just an empty file with the name while on node 5. We are going to verify this file when we move around. So okay, we created that file on that persistent volume. After that, what we are going to do is we're going to make sure that node 5 is not going to run this instance again. We are going to disable scheduling of pods or containers on node 5. Then we'll kill Cassandra -2 instance, and it will never get scheduled on node 5. That's what we want to show. So we want to show that persistent volume moves. Okay. So we should disable scheduling on node 5 and deleted Cassandra -2 and then recreated it. Now it is getting scheduled on node 3. We see that now node 3 is running 2 instances of Cassandra, and that's perfectly fine. If Kubernetes cannot find enough nodes, it's going to schedule second one on one of the previous nodes. On the left side, you will see that no newer volume is created. And on the right side, you will see that node 3 now has 2 block devices. So what is the second block device? Second block device is the block device which belonged to Cassandra -2 instance, but it's just moved from node 5 server to node 3 server. And we have just verified that it's the same volume because the file we created while on node 5, it's still there. So that basically tells us that when Cassandra or any stateful set application pod or containers, they move around, they run on a newer or a different worker node, storage travels with them without any manual work. This is all automatic. This concludes the demo. Now let's discuss what are some of the takeaways from this talk. So keep it simple. Stateful set applications can be scaled out quickly with network storage. Right? If you don't have network storage, then you cannot move around pods. You will have to look at the local storage, and then want to make sure that that the resiliency within application and then moving around and availability of worker nodes need to be maintained. But if you have a network storage, you basically don't have to worry about that. Leverage the capabilities of CSI driver. They not only offer like attaching, detaching, or creating volumes, but there are many other aspects like snapshot, cloning, all those aspects, right? Then the user-defined standards, depending upon the need, right? Whether you want to use RDMA or over converged Ethernet or TCP/IP. So NVMe over Fabric gives you performance of local storage and flexibility of network storage, right? And then some of the stateful applications, they provide resiliency within them, so that you don't have to worry about resilient volumes at the storage level. For example, Cassandra can save multiple copies of the data, and it can manage it, so you don't have to create replicated or mirrored volumes or RAID volumes and attach it to Cassandra. That's the whole purpose. Some of the references, they will you can click on them, read where I got some of the information when this presentation becomes available. I would love to talk. Any questions, please reach out. I'll be around. I'm here. You can directly reach me on Twitter.